Continuing our discussion of Chapter 2, we are in 2.6 where we're talking again about tangents, velocities, and other rates of change. You remember we talked about tangents and velocities back a couple sections ago, I believe in 2.4 now, or maybe 2.3. Now we have the concept of limit defined, so we're going to take another look at these tangents and velocities and use limits actually to find these tangents and instantaneous velocities. Remember what we're talking about when we're talking about a tangent. We're talking about some function y equals f of x and some curve generated by the graph of that function. So say that our function maybe looks like this. And to find the tangent, what we want to do is, we talk about the tangent line to a curve. We're talking about a line that touches the point, touches the curve at that point only, and is in the same direction as the curve at that point. And so this here is the tangent line to the curve, y equals f of x. And what we're interested in finding is the equation of that line. A lot of times we'll be interested in finding the equation of that line, and of course to find the equation we need to find the slope of that line. And remember how we did it back in 2.3. We said, all right, well here's some value x, or actually let's say that's some value a, and then let's add some onto it and take some point q. So we had maybe our point p is what we started with, and then we had our point q. We said, all right, well let's take the line between p and q. Let's call that m sub p q. And so remember what that's going to be. That's going to be the function f of x minus function evaluated x divided by, or minus the function evaluated a divided by x minus a. And then the slope of that line, that's m sub pq, is going to be an approximation for the actual slope of the tangent line. But that slope is going to get better as this q point, if we slide it closer and closer to the point where we're looking at, where x is equal to a. So this point right here you can think of as x comma f of x. This point right here we can think of as a comma f of a. And so we're going to find the slope between these 2 points here. We take the difference of the y values, f of x minus f of a, divided by the corresponding change in the x values, x minus a. And so what we're going to do then, as we said, is we'll get a better approximation. This slope will be a better approximation of this actual slope of the tangent line by letting q basically slide down here. Say we look at this line here. Well, this slope of this line is better. It's more closely approximate of the actual slope of the tangent line. So what we're going to do then is we're going to say, all right, well, let's go ahead and let x get as close as we want to this value a. When we use language like that, we can get arbitrarily close. We're talking about taking a limit. So we're going to say then that the slope of the tangent line, m, is going to be the limit as x approaches a of this slope sub pq, which again is the function f of x minus the function evaluated at a divided by x minus a. So we're taking the limit then as basically this point approaches the point here where x is equal to a, our point p. We're not considering when we actually get to that point, because when we get to that point, well, we don't have any difference, and x minus a would be 0. We'd be dividing by 0. We're just taking the limit as that point approaches it. Remember, we looked at a visual of this. It looks something like this. And remember what we said here is we have our tangent line is this yellow line, and we call it our secant line. Here's this line, the line PQ. And what we're trying to do then is look what happens as this point here approaches this yellow point. Now the H represents the difference between A, which in this case is 1, and X, which in this case is 2. And that H, that difference between A and X then, as it gets slower and slower, there's our limit going. And you can see then that the slope of the tangent line, now it's at 2.5, or the secant line is at 2.56, is approaching the slope of the tangent line, which is exactly 2, as h gets closer and closer to 0. In other words, the difference between the two values, x and a, gets closer and closer to 0. So that's what's going on here. And so we can formally define then the slope of this tangent line, m, as a limit, as x approaches a of f of x minus f of a, divided by x minus a. And so the book then defines in definition 1, it defines the tangent line. And here's the definition that we have. The tangent line to the curve y equals f of x at some point a comma f of a. This will be a given point, like 2 comma f of 2 or 3 comma f of 3. That's the line that goes through that point that has a slope that we talked about. The slope given by this limit of the secant line as that secant line approaches the tangent line. And you'll see then that this is all, of course, assuming that the limit exists that we're talking about. If the limit doesn't exist, then all bets are off, and we can't find that tangent line. So by way of example, let's go ahead and look at number 6, at least 6 part I of part A. 6 part A, part I. We want to find the slope of the tangent line to the curve here. Y is equal to x cubed at the point of -1 comma -1. So our A here is -1. F of A, which is f of -1, is -1 cubed, which is also -1. So this is our P point here with A being equal to -1. Using definition 1 in part I. So we're trying to find the slope of the tangent line. Now remember, the slope of the tangent line is going to be the limit as x approaches A. Well, A in this case is -1 of, let's see, f of x minus f of A, which is -1 divided by x minus A. So we have f of x is equal to x cubed, minus f of -1, which is -1, all divided by x minus a -1. So we actually have x cubed plus 1 divided by x plus 1. Now notice again, let's see, I get on you guys about this. We need to make sure we write our limit in each time here. The limit as x approaches -1. Notice we can't plug it in because -1 is not a part of the domain of this function x cubed plus 1 over x plus 1. We can factor, however, and factoring a sum of two cubes is something that well, you may not remember. I'm sure you've done it at some point or another. But x cubed plus 1 factors into x plus 1 times the quantity of x squared minus x times 1, or just x, plus 1 squared, which is 1. So we have that over x plus 1. And so this simplifies then into the limit as x approaches -1 of x squared minus x plus 1. And now this function is defined at -1, so we can go ahead and put -1 in, and we get -1 squared minus -1 plus 1, or we get 1 plus 1 plus 1, we get 3. So it looks like the slope of the line tangent to the curve y equals x cubed at -1, -1 is 3. Let's take a look at the graph of that and see if that bears out. So here's what we're saying then. The point -1, -1 on our curve here, if we were to draw a line tangent to it, we would have a slope of 3. And that looks to be about right. In fact, I'm kind of curious, what would the equation of the tangent line be at that point? And that's what we're asked to do in part B. So let's go ahead and find the equation of the line tangent to the curve, y equals x cubed at the point -1, -1, at this point right here. We have a slope of 3. We need just to find the y-intercept. So let's go ahead and do that. So we want to find then the equation of the line tangent to our curve of y equals x cubed at the point -1, -1. Now remember, we already have our slope. Our slope we found by taking that limit. The slope is equal to 3. How do we find the equation of a line? We're going through this point -1, -1 with a slope of 3, so we could use maybe the point slope form. Actually, let's use the slope-intercept form. I think that's what most people like to do better. Y equals mx plus b. M is equal to 3. We can put -1 in for y, -1 in for x, and solve for b. So we have -1 equals 3 times -1 plus b. -1 is -3 plus b. Adding 3 to both sides, we get b is equal to 2. And so our line tangent here is y equals 3x plus 2. Let's go ahead and graph that line on the same axis here. And 3x plus 2, we should see a line that is tangent to the curve at -1, -1. And there it is. Tangent to the curve at -1, -1. It touches the curve at that point and goes through a y-intercept of 0, 2. Now there's another common way of looking at the slope of the line. We said that it's the limit as x approaches a of f of x minus f of a divided by x minus a. A more common way, usually to define the slope of the tangent line is to let h equal x minus a. And that's what we did in that visual before. H is the difference here between our a value that we're starting at and the x value that's approaching that a value. So if we let h equal that difference between x equals a and just x itself, as x comes and approaches a here, well, let's see what we got then. If we let h equal x minus a, that also tells us then that x is equal to h plus a, or a plus h is how we're normally going to write it. So I'm going to replace x here with, in place of this x right here, I'm going to put a plus h. So I have f of a plus h minus f of a divided by, and in place of x minus a here, I'm going to put h. So we can say the slope of the line tangent to a curve at the point A is given by f of a plus h minus f of a over h, although we need the limit here. Well, as x approaches a, what does that mean? Well, as x gets closer to a, that means h is getting closer to 0. So we're going to take the limit as h approaches 0 of f of a plus h minus f of a all over h. Let's go ahead and look at 6 part a, part double I, to see if we get the same line tangent here. Y equals x cubed at -1, -1. So here our a is equal to -1. And we're going to take our slope of our line tangent to be the limit as h approaches 0 of f of a plus h. Well, minus f of a divided by h. Well, that's equal to f of 3 plus h minus, no, not f of 3, f of -1, a is -1 here, minus f of -1 divided by h, which is equal to, well, what's f of -1 plus h? Well, f is to take whatever you put into it and cube it. So we have -1 plus h quantity cubed, minus f of -1. F of -1 is also -1, divided by h. What does this give us? Well, if we cube this out, we're actually going to get, let's see, we get -1 plus h times, let's square this, we get 1 minus 2h plus h squared plus 1 all over h. And so we get, let's see, multiplying this through, we're going to get a -1 plus 2h minus h squared plus h minus 2h squared plus h cubed plus 1 divided by h. Alright, and again, I'm getting lazy with my limits. These should all have the limits as h approaches 0 on them. Limit as h approaches 0. The limit as h approaches 0 and the limit as h approaches 0. Now what happens here, notice we have a -1 and a +1. Everything else has at least one h in it, so what do we get? We get the limit as h approaches 0 of, let's see, 2h plus h. We got an h cubed. Let's start with that. H cubed. Let's see, then what else? We got minus a 3h squared. Let's see, plus 3h, looks like. All divided by h. Well, if we divide each of these terms by h, we have the limit as h approaches 0 of h squared minus 3h plus 3. This function is defined as a polynomial which has 0 as part of its domain, so we can just plug 0 in here. 0 squared minus 3 times 0 plus 3. And we get the same answer that we got before using the other definition of our slope of our line tangent. We got 3 that same way. So you're going to want to be able to use both those definitions to find the slope of a line tangent. Okay, the next topic we want to talk about then is velocities. And if we have s equals f of t, and we consider this to be a position function, position at time t. So in other words, let's think about what that means. Let's suppose that we have a graph of this function f of t, and let's suppose this is a graph of where you are position-wise t minutes into a trip. Well, so you start here at home, and then you are going, and then it flattens out, and it gets real steep, and then it kind of flattens out again and gets steep again a little bit. Well, so how far you are away from home, then, is the height of this graph. And you can see that if it's steeper, that means you've traveled farther over a shorter period of time, which means that you're going at a faster rate. If it's flat here, that means you're not increasing your distance away from home over this period of time. That means you're not moving at a very fast rate. In fact, the velocity that you're changing at is 0. And what you can see then is that the slope of the line tangent is actually going to approximate, it's going to give you exactly the velocity that you're traveling at that point, how fast you're traveling at that point, because actually the slope of the line tangent is going to be the same direction as the graph at that point. We can see that, for example, if we look at this function here. This is a function y equals e to the x, f of x equals e to the x. We're at the point 0, 1. The slope of the line tangent here is at 1. Remember, that's how we defined our function, e to the x. And what we mean by the function is in the same direction as the line tangent here. If we were to zoom in on this point, we would see that the graph actually looks just like the tangent line. If we zoom in here at this point, you can see that the graph here, e to the x, really is very well approximated by the line. In fact, they get closer and closer the more we zoom in. And you can see the more we zoom in, we're at 16 times magnification, 20 times magnification. Really, the line, the slope of the line tangent, is in the same direction as the graph, which is what we mean by that. And so we can see then that if the line tangent has a particular slope, that tells us how fast the graph is changing. And so the slope of this line is actually going to be the velocity at that time t. So we can define then the velocity at a particular point, say A. The velocity v of A will be the limit as h approaches 0 of f of A plus h minus f of A divided by h, which again was just our definition for finding the slope of the line tangent. So the velocity, if your original function is a position function, it tells you how far you've traveled at time t, then the slope of the line tangent at that point is going to tell you how fast you are traveling at that particular point. And then finally, we will conclude this video with other rates of change and just briefly talk about the last portion of the text that you read before you watch this video. If we have y equals f of x, well, we can measure, and we go from, say, x changes, so x changes from x1 to x2. Well, we call a change in something delta x, so we're going to let delta x equal that change in x. So it's going to be x2 minus x1. Well, then we're going to call delta y the change in the function value. So it's going to be the change in the function value at x2 minus the function value at x1. And so what you can see then is that this instantaneous rate of change, which is the velocity, which is the slope of the line tangent, is actually going to be equal to the limit as this delta x approaches 0 of the change in y over the change in x, which we can think of as the limit as x2 approaches x1 of f of x2 minus f of x1, remember that's what delta y was, over x2 minus x1, which is what delta x was. It's just basically a different way of saying the same thing that we have been saying. Let me draw a picture of it. So suppose we have a function y equals f of x here, and we have 2 points, x1 and x2. And what we can do then is draw the line connecting those 2 points. Now this distance here from x1 to x2, we're calling that delta x, the change in x. And the distance from, well, here is f of x1, and here is f of x2. That difference we are calling delta y, the change in function value at x2 minus the function value at x1. Well, notice that if we look at this as a triangle here, here is delta x, here is delta y. The slope of this line is equal to the change in y over the change in x, delta y over delta x. And so as x2 slides towards x1, and this point slides towards that point on our curve, this slope here gets a better and better approximation of the actual tangent line slope. So again, it's just another way to define the slope of the line tangent. All right, we'll look at some more examples in the next video.